Hi everyone, I want to talk about AC electronics now that we've got our three main components defined. This is kind of a simple example of an AC analog circuit. We've got an inductive ring here. It's just a spiral coil of wire. I can control its inductance with an iron core. I can increase the inductance by concentrating the magnetic field in this way. I've got capacitors here and resistors, and those three components basically drive every analog circuit that exists. So we want to talk a little bit about how these three components react to alternating current, alternating voltage. And that's what these three graphs here represent. On the top we've got resistor, capacitor, and inductor. The resistor here is simple. So we've got the voltage being driven by the source. It obeys Ohm's law, therefore the current is just a multiple, is proportional to the voltage. The pattern is exactly the same, it's just a little larger, smaller, depending on the R value. Now the capacitor looks quite a bit different. Here we've got a shift, and so we want to talk about why is there a shift. And it has to do with the way a capacitor works. A capacitor, remember, the voltage in a capacitor is associated with the charge that is on the capacitive plates. And so when the charge, so if the voltage on a capacitor changes, the charge on the plate is what changed. Now we know that current and charge are connected. Current is really the flow of charge, so when charge flows, when charge changes, current flows. So there's an indirect connection between the voltage and current in a capacitor, and that's what's driving this phase shift, that indirect connection. Remember that when the voltage changes from negative to positive, that's essentially a large change in charge. That has to happen because current is flowing into the capacitor, right? And so that's why the blue line kind of peaks at this point, is because that's when the maximum current is required to supply the charge to support that voltage change. And so that's why the pattern looks the way it does. When this is on the upswing, the current's maximum. When it's on the downswing, effectively, this represents a charging capacitor. This is a discharging capacitor. And the current follows that pattern as a consequence. Now, the inductor, there's a different story because the inductor is driven by Faraday's law. Faraday's law creates the opposite effect in the sense that a changing current, a changing magnetic field, induces a voltage. So in this pattern here, it's better to think in terms of the current driving the voltage. Even though in a real circuit the voltage source is what drives the whole circuit, it's kind of an exercise in philosophy about saying which is driving which is the cause and which is the effect. Really, it's just the whole system stabilizes into an equilibrium. But conceptually, I think we should think of the current driving the voltage in the inductor, and basically the current drives a magnetic field that's proportional to the blue line. So when the current changes, when we've got maximum change in the magnetic field, that's when we've got a peak in the induced voltage due to Faraday's law. And so kind of you have the same argument, but the colors are reversed. Here, the blue line, when the blue line's changing, we get a peak. When the blue line is decreasing, we get a negative, a trough, right? And so that explains why there's this phase shift in terms of a capacitor and inductor, the way they react to a source voltage. Now, which is in front of which is kind of hard to remember. That's what this ELI the ICE man represents. So E is connected to the electric potential. So for an inductor, the L, this is a capacitor, for the inductor, the voltage leads the current. The voltage peaks first. And that's what happens in this picture. Remember, time flows to the right. I screw this up every time. Time flows to the right, so stuff on the left is happening first. So here we've got the voltage peaks first, and then the current. ELI. Okay? But for a capacitor, it's the current that peaks first, then the voltage. So ICE is what is an easy way to remember that. So if you ever have to remember which is in front of which, ELI the ICE man tells you the answer. Now the one last component to talk about here, or one last element, is how big is this blue line or red line? You know, what's the relationship between the size? For a resistor, it's simple. It's just the resistance. Ohm's law is all there is to it. And here it's more complicated. It's associated with capacitance or the inductance, but also has to do with the frequency, because you know for both the current that supplies the current supplies is proportional to how fast the required change in charges. Faraday's law, the voltage is proportional to how fast the current changes. So not only do we have capacitance or inductance, but the frequency, how fast this is occurring, also has an impact on the size of the current or resultant voltage. And that's what these formula over here represent. They represent something called the reactance. It's kind of a AC generalization of the idea of resistance. It's the proportionality between current and voltage for these different sources, for these different components. So it's traditional to represent reactance with the letter X. So in fact, I shouldn't show it this way. The reactance is really just for the inductor and capacitor. We have pure resistance for a resistor. So pretend that's not there. But the reactance for an inductor is given by this formula. Why these go that way? I should fix this slide. So for an inductor, it's just 2 pi FL. And this is, this is associated with the electric generator formula. If you want to go back and look at that formula, that's where this comes from ultimately. For a capacitor, it looks very similar, but it's got the reciprocal. So we've got 2 pi F C in the denominator of the reactance. And that's how to determine the relationship between the peaks on the red and the blue lines. And also, because that's the relationship between the peaks, it's also the same relationship between the RMS voltages, which we measure in the laboratory. So these formula work for either situation. If we're just measuring stuff in the laboratory, this gives us the relationship between those measurements.